Hello and welcome to Team 11's presentation for MEEM3901 covering the design and analysis of a rack and pinion conveyor cart. In this project, the team was presented with a generic problem of a horizontal mover needing to move a mass of 250 kilograms through a multi-stage duty cycle. In order to explore various mechanical solutions to this problem, the team created several SimCenter AIM-Sim models to model different mechanical devices that could accomplish this motion. Moving forward, for more detailed simulation, the team decided on a moving sidewalk approach. However, we used a cart to model one segment of the conveyor belt for simplicity. In these further, more detailed simulations, we analyzed various variables such as peak acceleration and jerk, power usage, and the time taken to move throughout the duty cycle. Finally, a hypermesh FEA analysis was performed upon the back right wheel, which was the driven wheel, in order to identify potential physical limitations of the system.
Next, we have the hard requirements table. The requirements listed here are for acceleration, jerk, cart mass, power, useful life, and time between stops. The target values were determined from the industrial standard ASCE 2113. The actual values were determined from SimCenter AIM-Sim and MotionView models, and the met requirements can be denoted by green boxes. It was determined that the maximum acceleration experience was 2.29 meters per second squared, which was less than the target value of 4.57 meters per second squared. The jerk was found to be 0.1 Gs per second, which falls within the range of less than 0.1 Gs per second. The utilized mass was 250 kilograms, which falls within the range of 100 to 500 kilograms. The maximum power was 60 volts, which fell within the range of 0 to 60 volts specified by the target values. And lastly, the time between stops was 16.67 seconds, which falls within the range of 0 to 16.67 seconds set. Lastly, there's useful life, which is yet to be determined.
Using the hard requirements Kyrie just mentioned, we had to design a model that represented a conveyor belt moving a general mass over a defined distance. We started with a magic force block to understand the basic concepts of AIM-Sim. From here, we chose a rack and pinion as our model to be our real force. Starting on the left side of the model, we see the user-defined duty cycle. This tells how far we want to move our mass. Moving to the right, the U-shaped icon is the voltage. The voltage comes from the user-defined duty cycle. Moving down to the motor, the voltage creates the power. We then use the gearbox to create a torque from the power. The rack and pinion creates a force from the torque, and the force moves the mass along. From the displacement we get of the moving mass, we then send it back through the loop to tell how much more force we need to get to our defined spot. And then the loop just starts all over again.
I'll be talking about the MotionView model and ensuing result. In Figure 1, we can see our horizontal mover with our mass block on top in MotionView. It is driven strictly off of our motor, which drives the entire mover. As can be seen in the figure, the wheel attached to this motor is our critical component, which Joe will touch on more in a bit. We uploaded the velocity from the original AIM-Sim data, which is then transitioned to the motor and from there to the rear right wheel with transitional joints, causing the walking sidewalk to move. Next, looking at Figure 2, we can see our duty cycle, MotionView, and AIM-Sim position data. The AIM-Sim and MotionView data line up nearly perfectly, as should be expected with the AIM-Sim data being imported into our MotionView model. However, we can see that we vary slightly from the duty cycle, and this is mostly due to the fact that we wanted to keep from accelerating too much and making sure that we met our original hard requirements.
For the FEA analysis of a critical component, we decided to go with the driven gear wheel as it's under power and what's required to move the whole cart forward. The material we decided to model it after was steel with a Young's modulus of 210 gigapascals. The forces acting on the wheel were derived from our MotionView model with a peak torque seen as it's about 100 newton meters, and the weight of the cart on the wheel was 85 newtons. Both were applied on the cutaway face of the axle with a RB3 model. and the bottom face of the wheel was fixed in place to simulate rolling without slip. The max displacement was seen on the top free edge of the wheel, which is what we would expect if the model is accurate, and that max displacement was 7.14 to the negative 3 millimeters, which is essentially zero, and the peak stress in the wheel was seen around the outer surface of this axle, and it was about 36 or 32.6 megapascals, which is relatively in line with our hand calculations, which turned out to be around 23 megapascals. It's within a margin of error, as we were kind of just loosely estimating the numbers for the hand calculation.
In conclusion, our cart successfully met all the requirements that we had predetermined from the standards we located. This can be quantified through our simulations in various software, be it Hypermesh, AimSyn, or MotionView. This design could easily be implemented to make a real people mover cart work with its scalable design and simple setup. To further improve, we could reduce our stopping time, but overall that would be hard to achieve without a complete braking system, which would be very complex. We could also try to reduce the power or increase the allowable payload, but those would both be fighting each other with their inverse relationship to each other.